You start, sir.
Okay, sir. Yeah, good morning, children. I'm back to the last concept, that is magnetism matter, and in that we stopped at the middle of the angle of declination, right? So we'll continue here that the angle between the magnetic meridian and the geometrical meridian at a particular point is called angle of declination, which is passing through at that location. So here we should understand what is magnetic meridian, already we discussed, and geometrical meridian. So meridian is what? The line that is passing from north pole to south pole. If that north pole is magnetic, so from magnetic south pole to magnetic north pole, that is magnetic meridian. Similarly, if that north pole is geometrical north pole, then the line which is passing from geometrical meridian, that is from geometrical north to the geometrical south, then that is geometrical meridian. Okay, so actually it is a geometrical axis and magnetic axis, but it is a surface. If we may cut that into surface area, then that part is a meridian. So here you can see the picture. See the blue line here, so that is magnetic north pole, right? And the yellow line is to the geographic north pole, right? So the person is watching these two from this point. For that person, it makes an angle between this geometrical north pole and magnetic north pole. So this angle is called angle of declination. Angle of declination. And remember, this angle is not same for all the points on the earth. Means from different places, the angle will be different. So this value is not same for all the people, means all the places who are observing this magnetic north pole and geometrical north pole. So the value of this declination changes from one place to another. So this was already discussed in the last class. Now coming to magnetic inclination or dip. Magnetic inclination. Yeah. So here the angle between the intensity of Earth's magnetic field and horizon, that is the surface of the Earth, is called magnetic inclination. Magnetic inclination. See here, try to understand the concept here. Here in this figure, if you observe, this is a magnetic compass. This shows only the direction of north pole of the Earth. I am repeating, this compass needle always shows the direction of Earth's north pole. Okay, if it is suspended like this. Now coming to this figure, see if the magnetic needle is in this way, means the pivot is like this, then it will move up and down. It will move up and down. But here, just it will oscillate left and right. It will oscillate left and right. That's it. But in the right side figure, if you see that it is moving up and down. Right? So here, already we discussed in the last class that when the magnetic field is very strong, then the magnetic needle attracts towards that. Yes, here is by holding the compass in your hand like this. So for example, this is a north pole. Now you are holding this and moving towards the north pole of the Earth, walking towards. And at a point, at a position, you are reaching that North pole, exactly North pole, then it shows the downward direction. The needle moves downward direction. Means what it says, this deflection, this tiltness shows that here at this point the magnetic field is very strong. Okay, I'm repeating, when you are walking from the equator of the earth, it shows like this only, it shows only the direction north pole. Now you are keep on moving and reach the north pole, and there the needle deflects downward, that is vertically downwards. So what it says that at that point the magnetic field is very strong. So that's what here we are using this point, that is intensity of X magnetic field. Intensity of X magnetic field. So always the X magnetic field is horizontal, and the tiltness of this magnetic needle is downward. The magnetic needle is downward. If the field is normal, then it will show only like this. But if the field is very strong, the intensity is more, then it will move downward. So it is making some angle. So this angle between this magnetic needle and the magnetic needle to the horizon, the surface of the earth. Okay, so the angle between the intensity of X magnetic field and the surface is called magnetic inclination or dip. So here you can see the diagrams here. So this dotted line is what? The horizontal surface of the earth, and this is the tilted angle, that the magnetic needle is tilted, and this angle is called inclination. That is magnetic inclination or dip. And here the same conveyed in the other way using this diagram. The magnetic needle is allowed to move in a vertical direction when it shows the intensity of X magnetic field. Yeah, that's what we discussed. Okay, wherever the magnetic field is strong, the intensity is more, then the magnetic needle shows, that is compass shows the vertical direction. And the angle, it is tilted. The angle, it is tilted, shows that strength of the magnetic field. That how much angle it is tilted, that shows the strength of the magnetic field. Okay, so here if you observe this diagram, the front face, just the whole discussion is given in a single diagram. The whole discussion is given in a single diagram, that this front face of this diagram is just, let us consider this is as a magnetic meridian. Okay, one part. And you are standing at this point. And another direction means this dotted line means other plane if you observe, that is geometrical meridian. This is geometrical meridian, and the front face is magnetic meridian. And the angle between them is a magnetic declination. And now observe this. Let us take this magnetic meridian as a surface. This is a surface. Observe this diagram. See, on this we need to discuss one more topic. Okay, observe this diagram. So this horizontal one is a surface of the earth, for example. Okay, horizontal one is the surface of the earth. Then downward is a vertical component. And meanwhile, you observe this line. This is the magnetic field. Now, the angle between the horizontal surface of the earth and the magnetic field direction, the angle between, observe these two lines. This is the magnetic field direction and this is the earth's surface. And the angle between them is angle of dip. Okay, the same discussion here in this diagram. What is that? It's a horizontal surface and the needle is dipped. Needle is inclined. So this angle is called angle of dip. That's what is given here. For example, this is the surface of the earth and this is the direction of the magnetic field, and angle. Direction of the magnetic field means what? The direction of inclination. The compass is inclined at such an angle. Okay, so this angle is called magnetic inclination or angle of dip. See, if you understood this one, the same diagram, on this same diagram, we are going to discuss one more important topic. Okay, I hope you understood. I'm repeating this. The person is standing here and observing the whole system. Okay, I told you that person to person, this magnetic declination changes. Magnetic declination changes. So in the single diagram, the two concepts are shown here. Okay, so from the horizontal surface, this magnetic field is making angle. So that angle is called angle of dip, and the angle between this magnetic meridian and the geographic meridian, that angle is called magnetic declination. So observe this, and we are going to discuss this delta concept. We are going to discuss the delta concept. Okay, so we'll move on to the next. Yeah, see here the angle of dip can be measured. The angle of dip can be measured by using a device called dip circle. This is actually the device that we use to measure how much angle is there between the surface and the magnetic field direction. Okay, so first of all we need to draw a magnetic line of force, and keeping on that, this device is keeping on that line. Then to this, how much is shows some direction, some deflection. Okay, so that the angle that we can measure, this is dip angle between the surface and the magnetic force direction, that is intensity of magnet. Okay, so this is what is a dip circuit. Is a device to use to measure the angle of dip. Yes. So this is I told you that the diagram will be repeated. Yes. Here, observe this dotted line, is horizontal line is a magnetic surface. Horizontal line is a magnetic surface, and this needle is inclined and gives the information that how strong the Earth's magnetic field is. So that is inclination or dip. Now observe this graph, this diagram. So this is the Earth here. Okay, Earth. Now when we move away from the Earth, magnetic field decreases. Definitely the magnetic field changes, that is decreases. I'm repeating, when we move away from the Earth, the magnetic field decreases. This line, this inclined line, is a magnetic field, means line of force. Magnetic field, that is a line of force. This is making angle with the horizontal surface of the Earth. Okay, this BH indicated as a BH means magnetic field along horizontal direction. BH means what? Magnetic field along the horizontal direction. Means what we have done here, this inclined one is a magnetic lines of force, that is magnetic field. That is magnetic field is resolved into two components, that is one is horizontal component and other one is vertical component. That is magnetic field along vertical direction is indicated with a dB, B suffix of B. And similarly, the magnetic field along horizontal component, horizontal direction is indicated with the BH. So what we have done here, this is lines of force, that is line of force of means direction of the magnetic field. So this is indicated as B here. So this B is resolved into two components, one is horizontal and other one is vertical. And this B means what? Horizontal component is making angle with the this one magnetic field. Let us take is pi, theta, whatever. In different books gives different notations. We can use delta, we can use theta or pi. Okay, so here this angle is what? Is an inclination or a dip. So with the surface, magnetic field is making this much angle. This is what? Dip angle. Okay, now this BH plays a very important role because this value is more considered for doing so many experiments on the earth. Okay, on the surface of the earth, this value is playing very important role, because if we consider this vertical component, when the position changes vertically upward, then the B value changes. Whereas BH value is along the horizontal direction, almost the B value will be nearly equal, nearly same values. Means this affects while doing the experiments in the laboratory on the surface of the earth. This we calculated as 10 power minus 5 Tesla, that we already calculated. So here this value is changes, so we won't consider this, but along the horizontal direction we are considering BH value. Okay, so on this we are going to derive the next concept. Yeah, here is this, whatever we discussed. Here we can resolve the Earth's magnetic field strength in two components. Yeah, understood? I hope you all understood. See, the magnetic field, magnetic lines of force which are of the Earth, and these are resolved into two components, horizontal component and a vertical component, and we are focusing on horizontal component now. So we can resolve the Earth's magnetic field strength in two components, that is, along the x-axis, the horizontal component will become BH. B sub x means magnetic field along horizontal direction. Magnetic field along horizontal direction is B cos delta. Here, what is delta here? Delta is the angle of dip, that is angle of inclination. And here B is the magnetic field. And cos theta means cos delta. Cos is what? This is making along x-axis. Theta is making along horizontal direction, so it will indicate with the cos here. So here, and along y-axis, vertical component, that is B suffix B, that is vertical magnetic field along vertical direction is B sin delta. Now, just divide these two, then we will get dB by dH, that is equal to B sin delta by B cos delta, that is tan delta. Okay, so dB by dH is equal to tan delta. So the ratio of magnetic components, magnetic field components, vertical by horizontal, you are getting tan delta. So here from this we can calculate dB, so magnetic field along vertical direction is, this is an expression. That is, magnetic field along vertical direction is equal to the product of what? Angle, tangent of what? Delta. Here what is delta? Don't forget, this is a dip angle. And dH is the magnetic field along H direction, that is horizontal direction. Right? So with this we can calculate, means we can estimate the amount of magnetic field along vertical direction, and also we can calculate the total amount of magnetic field strength of the Earth, also we can calculate this in this form. So here we can also calculate the amount of magnetic field strength. Okay, amount of magnetic field strength with the same diagram, here. So if you want to calculate the resultant of this magnetic field, you already learned that is a parallelogram law. Okay, so resultant of this is under root the two components, that is BH square plus BD square. Okay, so two components. If you know the values BH and BD, then we can calculate the net magnetic moment, that is total magnetic field strength of the Earth, can be calculated using this formula. Okay, so this is about the big bang. Okay, next, yes. I hope you understood this, the three components that we discussed. That what were that? Three components, that is magnetic declination, magnetic inclination, that is a dip, and horizontal component of Earth's magnetic field, that is pH. Okay, so if these three are comfortable, means you are understood well, you can attempt the question. If the question is asked as a long answer in the final examination, so elaborate these 3 points with the required diagrams. So I hope you understood it well. Okay. Then we'll move on to the next a small concept, that is time period of an oscillation. This already you have learned in the first year of right? Right. So here, because it is there in our portion that we need to obtain the expression for the time period of magnetic deflection, that is magnetic oscillation. So let me explain this diagram once. Then we will move on to concepts. Just let me explain the same concept that so far we discussed here. Relates. These long arrow marks are what is magnetic, uniform magnetic field. Okay? Uniform magnetic field. In that, if you are keeping one a small magnetic needle, but here just so it's correlated, of course, don't you worry. That here this is a magnet is given, but originally we'll start with what is a magnetic needle. Magnetic needle that always directs towards the direction of magnetic field. See, observe this direction of magnetic field, arrow mark, this is uniform magnetic field. And in that field, if you are taking any magnetic needle, that always directs towards, means aligned towards the direction of magnetic field. Okay, then now if we made some angle, means if we twisted that, if we see this is the magnetic field, see magnetic flux is going, okay, then this is the magnetic needle. Then if you forcibly bend like this, twist like this, see this is in the magnetic field, it is aligned in the magnetic field along the direction of magnetic field. Now if you forcibly twist like this, if you twist like this, then what happens? Then it's making some angle into the direction of magnetic field. Then look at this diagram. Then two forces. One is this side force is acting, that is MB. How much force it is? Magnetic moment into B, magnetic field. So that is the product of pole strength into B. That gives the magnetic force this direction. And as when you twist it like this, and the opposite force is also action that this side is also MB. So total force, equal and opposite forces acts on this magnet or needle. Then a torque, the phenomenon is torque starts acting on this magnet or magnetic needle. Okay, so when you made some angle, then some couple acting on the force, the two forces, two equal and opposite forces acts on that to restore, means coming to its, it comes to original position. Initially, it was aligned to the along the magnetic field, but forcibly what we have done, just we made twisted with some angle, then two forces are acting at the poles. Those are, means that is termed as torque. Now observe this. See, this is an angle made with the applied field direction. Observe this diagram. This dotted line is the magnetic length, okay, magnetic length, that is 2L. Magnetic length is 2L. Now this is inclined. See, observe as per the parallelogram law, this is 2L is the length, then it is making angle like this, then along the x-axis, along the horizontal, this angle means this side will be 2L cos theta. And whatever this vertical component will be 2L sin theta. I am repeating, according to the parallelogram law, this is what is the length of the magnetic length, and this magnetic axis is making angle with the direction of magnetic field, and this horizontal component means we are resolving this. Okay, we are resolving. Now along the x-axis it will be 2L cos theta, and along y-axis it is 2L sin theta. Okay, 2L sin theta. Now from the 2 points, from the 2 forces, north direction is one side of the magnet, the other side of the magnet. Two forces are acting, that is MB, MV in opposite directions. Those are the forces. Now, look at this right here. From the figure we know the torque is equal to force into perpendicular distance. So this is a physical quantity, that is a torque. So torque is nothing but force into perpendicular distance. Here, which force is acting here? Which force? That is MB. Two forces are acting now. MB. Which force? Force. And is always perpendicular to this distance. Perpendicular to this distance. So that is how much it is, 2L sine theta. So here is the expression we are written here, that is force into perpendicular distance is this. So that's why use this diagram. See, already you learned this in oscillations concept, that is simple harmonic motion or oscillations concept, that you understood that 2L sine theta is the perpendicular distance. So torque is equal to force into perpendicular distance 2L sine theta. So a total force is nothing but MB, okay, MB into 2L sine theta. So already that you know F is equal to MB. If it is in a electric field, it will be QE. QE. Q is the charge and E is an electric field. And here is the whole strength and the magnetic field. So F is equal to MB. Right. So look at this. B into 2ml sine, just read it in this expression as well, this 2ml. Okay, so this is bracket term that we can write as a capital M. So look into the next line, the torque is equal to Em sine theta. So when M is 2ml, that is magnetic dipole moment. That is magnetic dipole moment. Okay, so torque is equal to Bm sine theta. See, here we are discussing to obtain the time period of an oscillation. Time period of an oscillation. Okay, so here in this expression, torque Bm sine theta, where B is the uniform magnetic field and M is the magnetic dipole. Right? See, here observe this, due to inertia. Yeah, this point is to be understood. See, just here we obtain the torque expression. Now, this needle won't be at the same position. It won't be at the same position. It will, the moment it is reaching the maximum angle, that is maximum tilt, maximum twist, then if you leave it, then what happens? It will come to equilibrium position and crosses that equilibrium position in the other direction, in the negative direction. Okay, oscillation means what? See here what you have done. Initially it was like this, and you made force B with a certain angle, then you leave it, then what happens? It starts rotating, it starts oscillating, So this is equilibrium position, and you made like this, and you leave it, then what happens? It reaches the equilibrium and crosses that equilibrium, and starts oscillating. So this oscillation is due to inertia. So due to inertia, the needle continues to oscillate with angular acceleration. Okay, so this needle starts moving to and fro motion like this with reference to the equilibrium position. With respect to the equilibrium position, it moves up and down. Okay, to and fro motion. So this is because of inertia. It won't stop suddenly at the equilibrium. So the needle continues to oscillate with the angular acceleration, that is alpha. Then according to mechanics, okay, mechanics that we studied in the first year, any rotating body is possessed with both moment of inertia and angular acceleration. So these points to be understood. Remember that whenever the body is under a rotatory motion or oscillatory motion, then that body is endowed with both the physical quantity, that is moment of inertia and angular acceleration. Okay, because of the inertia, it started oscillating to and fro motion, and as per already we discussed in the mechanics in the first year, that any oscillating body is with the moment of inertia and angular acceleration. And with respect to this information, we have another equation, that is torque is equal to I alpha, yeah. Okay, so here I is the moment of inertia and alpha is the angular acceleration. Okay, so this is equation number 2 is from the mechanics that we studied. And equation 1 is due to this magnetism. See, just with an experiment, we have obtained this magnetic torque here. Okay, so Bm sin theta is the vibration we made. Okay, this is the torque we get from this concept, and this torque is from the mechanics that whenever the body is under oscillatory motion, then it is consistent with the two things, that is moment of inertia and angular acceleration. So equating these two equations, then I alpha is equal to mv sin theta, and here we are trying to omit sin theta values for very small values. Sin theta will become, we are rewriting that as in theta value, very small values. So from this expression we are obtaining alpha is equal to mv sin theta by I. So this is acceleration at any angle. So this expression is acceleration at any angle. See here, if the angle is more, see this acceleration depends on what? See, it's like a simple harmonic motion. Simple harmonic motion. So that is what simple harmonic motion is what? Moving maximum angle is what? It's a maximum acceleration. Okay, so theta is a more important role here. So here this alpha is equal to, just we are rewriting this expression in this way, that is alpha is equal to something, that is k into theta. I told you, so that sin theta we are rewriting this as a small values, theta here. So alpha is equal to k theta. So here k, just all these are constants, magnetic field, moment of inertia, and magnetic moment, dipole moment, all are constants for a particular magnet and for a particular angle. Okay, particular magnet, because I has a specific mass and a specific length of that magnet, and so that magnetic moment will, dipole moment will be the same, and it is produced in the fixed amount of magnetic field. So these three are the constants here. So we are just replacing this as k. Okay, so alpha is equal to k into theta. So in this expression, what we can understand, this alpha value totally depends on this angle, at what angle that we twist. Okay, right. So from this k is equal to alpha by theta. Just we obtain this expression, constant k is equal to alpha by theta. Right, so here alpha is nothing but acceleration. Alpha is nothing but acceleration, and theta is nothing but the angle that is displaced. The magnetic needle is displaced at what distance? That is angle. Okay, displacement. So observe this equation 3, that is k is equal to alpha by theta. Okay, where alpha is the acceleration and theta is the displacement. Now, already we know from the simple harmonic motion, the time period is expressed as, okay, so this is an expression for the time period. T, time period is equal to 2 pi into under root displacement by acceleration, under root displacement by acceleration. So here, substituting these values, that is theta and alpha in this expression, yeah, here is the formula. Time period is equal to T is equal to 2 pi under root theta by alpha. Okay, this is the time period expression, and substitute these values here. So let us do this calculation out of this root. So theta by alpha, that is theta by alpha, that is theta by, just now we calculated, alpha is what now? Alpha is what? K theta. Alpha is what? K theta. Yes, sir. So K theta is equal to alpha theta. So just in the place of alpha, we are taking K theta, and this theta and K theta will be cancelled here. There is 1 by K. That is equal. And already we know the K value is, what is that? mv by I. So 1 by mv by I. So it will become I by mv. It will become, yeah, I forgot to keep the is equal to here. So here I by mv. So now substitute this theta by alpha value in this root. Okay, right. So theta by alpha value, now we are substituting this in this root, that is time period T is equal to 2 pi under root I by M. So this is very important on this. So many problems will be asked, especially in IP. Definitely, I hope one question will be asked this time. So this is time period T is equal to 2 pi into I M. Okay. Now we'll see some problems on this. So with this, all the topics almost we completed from this chapter as per the syllabus. Means after deletion of some concepts from this chapter, almost we completed all the concepts. Now we'll do some problems on this. See, look at this problem. Of course, all are almost from your textbook problems only. So, if the horizontal and vertical components of the x magnetic field are equal at a certain place, then the angle of dip at that place will be. I am repeating. If the horizontal and vertical components of x magnetic field are equal at a particular place, then the angle of dip at that place will be. I hope you understood. Okay, X magnetic field already is I told you no, our diagram needs to be understood well. So that X magnetic field is divided into two components, that is horizontal and vertical. Already we discussed in the derivation part. So now what is asking? Find the angle of dip is asking. Means angle between the X components, that is vertical component and horizontal. Now look at this solution that you can understand, right? If you understood the concept, the ratio of dV by dH is equal to the ratio of dV and dH is equal to 10. So here I use theta, and then our derivation we use delta. Okay. See, for just I am given only as per the IP level, okay, but in the MSET and IT level, that the hardness of that is very composite, means very tricky questions will be asked. Means the concept, if you understood thoroughly the concept, if you understood well, then you can easily solve. Okay, so I hope you understood here. So here we know along the x-axis, the horizontal component is that I explained. BH means magnetic field along horizontal direction is b cos theta, and along y direction it is BV is equal to b sin theta, and this is given in the problem equal. Okay, both are equal. So both are equal means what? Here it's given in the problem that BV is equal to BH. And we know this is already a ratio that dV by dH is equal to tan theta, and as both are same, then it will be equal to 1. Then theta is equal to means tan. 1 means what? The 45 degrees. So theta is equal to 45 degrees is the angle. So this is an angle at which when both the components, both vertical and horizontal components are same. You will see one more problem. Yeah. The coil of 20 turns has an area of 800 millimeters square and carries a current of 0.5 ampere. If it is placed in a magnetic field of intensity 0.3 Tesla with its plane parallel to the field, what is the torque that it experiences? Yes, it is asking to calculate the torque here, right? So here, what information is given? The coil is there, it has 20 turns, and the surface area is 800 millimeters square is given, and which carries the current at 0.5 amperes current is flowing through this. And if it is placed in the magnetic field of intensity, so this whole setup, the coil, okay, 20 turns coil of air across the area of this thing, and the amount of the current which is flowing, the whole setup is placed in the external magnetic field of intensity is 0.3 Tesla. Okay, how they are tested? The parallel plane. The plane is a parallel field, means in which direction the field is moving. In parallel to that, only this whole coil is kept in that field. Then is asking what is the torque experiences. So here angle is very important. Okay, so this is the given information just I wrote here. And here it is given me, no, I converted that like this. Right, so angle between the plane and okay. Right. So the angle between the plane and the field is 0 degrees, that's parallel. So now here is the formula that, here is the formula, with that tau is equal to Bina cos theta. Formula, tau is equal to Bina cos theta. What is that B here? B is the magnetic field, the uniform magnetic field. I is the amount of current which is flowing through the coil, and N is the number of turns in the coil, and A is the area of that coil, circular coil. And cos theta is the angle between the plane of the coil and the direction of magnetic field. So substituting all the values here, that is 0.3 into I is down to 0.5 into number of turns 20 into the area, and cos theta, cos 0 is 1. So substituting all the values, you are getting this value, that is how much is 2.4 into 10 power minus 3 Newton meter. Okay. So this is the way to write, attempt the problem in the IT. That's we need to elaborate. Okay. Right. We will move on to the next problem. So a magnet, when it is placed, a magnet, when it is placed perpendicular to a uniform magnetic field of strength 10 power minus 4 Weber per meter square, experiences a couple of moments 4 into 10 power minus 5 Newton meter. What is the magnetic moment of the magnet? Okay, what is asking? Magnet when it is placed perpendicular to the uniform magnetic field strength. So magnetic field strength is given. Magnetic field strength is given. Okay, capital B is given. Experiences a couple of moment. Couple of moment is nothing but torque. Couple of moment is means rotation. Is rotated. Okay, torque is acting on that magnet. The magnet is placed in the actual magnetic field. So this magnet undergoes some torque. How much it is? 4 into 10 power minus 5 Newton meter. Okay, force into this place, perpendicular. And what is asking? What is the magnetic moment of that magnet? Is asking. Dipole moment. Magnetic moment is asking. Sorry, magnetic moment is asking. So here is the given data that magnetic field is given 10 power minus 4 Weber per meter square. And the torque is given 4 into 10 power minus 5 Newton meter, and the angle between the plane and the field is given perpendicular, so magnetic is, and magnetic moment that we need to calculate. And we have the formula tau is equal to mb sin theta. Tau is equal to mb sin theta. So take out m. So this is this thing that we need to calculate. So take out m value. So m is equal to tau by b sin theta. So substitute the values here. Okay, so sin 90 is 1. So that's why is the 1 multiplied with 1 here. B is given here 10. Where is B here? 10 power minus 4 here. And tau is already given 4 into 10 power minus. So together we are getting 0.4 ampere meter square is the magnetic moment.
Narsimha sir.
Sir.
Yeah, conclude the session, sir.
Yeah, sure, right. So with this problems will be like this. You can do using this formula time period also. Okay, so right on these assignments, why the magnetic line folds are continuous and closed doors. Okay, textbook questions only, but we're expecting more important these. Okay, so define magnetic inclination and magnetic declination. What happens to the composite let the X suppose, and define the terms magnetic field, magnetic susceptibility, and magnetization. And these are long answer questions with the need diagrams, whatever we discussed today's concept, that is elements, that is declination, dip and all, okay, and show the relation between the components of X magnetic field, okay, with a diagram, and you need to explain. So with this, we will conclude this chapter. So this chapter is completed, and in the next class we'll start with the new chapter, that is chapter number 9, that is electromagnetic induction. Okay, so thank you all.